So this morning, I'd like to start by talking about the safety aspects of hydrogen. And when I look back to the 1960s, and NASA decided that they needed to put a man on the moon and bring him back safely, they had they had many challenges, but two of the biggest challenges were the first, how to get man off of Earth and into space, and the propulsion requirements, and secondly, how to keep the man and machine safe during that journey. So how did they solve those two questions? Well, the first was hydrogen, the use of hydrogen and oxygen to provide the propulsion needs.
Now, in rocket A, we have 2 grams of petrol. In rocket B, we have 2 grams of hydrogen. We're going to find out which produces the biggest bang. Serious science, this. So, first up, petrol. Lovely, explodey petrol. Okay, and now, hydrogen. It's a clear win for hydrogen.
So we've solved the first problem with hydrogen. The second problem was batteries. Batteries at the time were very, very heavy, which added to the first problem. But secondly, they didn't have the lifespan and keep the charge for the length of the journey. So again, they turned to hydrogen. So NASA developed a hydrogen cell with a company called Pratt & Whitney that allowed them to generate the power. That same company has changed hands a few times since then, but has resulted in a company in Korea, Daesan Hydrogen Company, who are now making 50 megawatt plants that will power 160,000 homes. So NASA, back in the 60s, was responsible for a lot of everything that we see here today. So the good news is the risks of hydrogen are not new. We've been using hydrogen in refining, in chemicals for decades. But what we must do, and we must ensure that we do not make the same mistakes of the past. Let's leverage and capitalize on everything that we've learned and everything that we know about the safety and the safe use of hydrogen. And the good news is there's lots of experience and expertise out there to help you do that. But really the two key findings, the two biggest mistakes of all the safety incidents and events have been use of metal and venting. If you look back, a lot of the root causes. So we're in this transformational period of new energy, and there are new technologies abundant now, but those new technologies bring new risks, new threats. Obviously, from the energy generation, from the power generation side, through to the hydrogen mass production, the storage, the distribution. But really the incident, the consequence comes down to fire, explosion, electrocution, and maybe a little bit of suffocation in there. But I would like you to remember 4 things, only 4 things from my presentation today. The following questions: what can go wrong? What is the likelihood? What is the consequence? And what is required to reduce those risks? And remember, the consequences are not just safety, harm to people, but also to the environment and commercial. Remember those 4 things. So as you walk around, remember those 4 questions. What can go wrong? What is the likelihood? What is the consequence? And what do we do to make sure that doesn't happen? And electrolyzers. Now, electrolyzers are tricky little rascals, simply because we've got the 2 things that we don't want next to each other. We've got an ignitable gas source with a very low explosion limit and a spark from an electrical system, because we're using high energy and high demands. Those 2 things, from a safety perspective, are not a good mix. So here is an incident that happened recently, and you can see what happened when oxygen got in with the hydrogen, and all it needed was one little ignition spark, and this led to a loss of life. So it is real. Pay attention around the electrolyzers. What can go wrong? What is the likelihood? What is the consequence? What can I stop from happening? So if we look at the hydrogen value chain, and I'm just going to focus here for a minute on the production part of the process. So typically our plant is split between two. We've got the electrolyzers themselves, and we've got the balance of plant, the water, the power, the batteries, the cooling, the compression facilities, the storage, all of those ancillaries around the outside of that electrolyzer that we have to control and manage and keep safe. And typically, we're looking at things like high pressures, low pressures, flows, pressures, temperatures, highs and lows, basically, to make sure that nothing happens in that production or that balance of plant process. So keeping those processes safe is not an easy task, but the good news is we do know how to do it. So as you can see here, and the good news is I won't go into all of these details, I'll only pick a few. There is a lot required to keeping a hydrogen process, production process safe. Right at the very beginning, at the very design phase, through to the build, through operations and maintenance throughout the life. I'm going to pick on three things. I'm going to look at the hazards, risks and threats. I'm going to look at the electrical side, and I'm going to look at the safety side. So, the very, very first thing, what can go wrong? What are the hazards? What are the risks? What are the scenarios? Typically, we have a very systematic approach to managing doing that. We use that same approach for the process. We take the process, we break it down into nodes, we ask a team of questions. What could go wrong? What is the likelihood? What is the consequence? But the threats nowadays are no longer limited and constrained to just within the production facility. No conversation happens without cyber threats. They are real, they are more rigorous, they are more frequent. So what do? We take the same systematic approach that we do for process safety risks, and we apply it to a cyber. What are the threats? What are the risks? What are the consequences? And what do I do to manage those? But we don't just stop there, because it's not just the process and cyber. We've got this close correlation with all the electricity generation side and the power generation side. So we take the same systematic approach again, and we look at our electrical side. We break that down into nodes, high voltage, medium voltage, low voltage. We ask ourselves, what can go wrong? What is the likelihood? What is the consequence? So we don't just limit our thinking to be the process. We think about cyber, and we think about the electrical side. So we really are looking at everything that could potentially go wrong. But then, those are normally static exercises. They're on paper-based drawings. Now we can make them dynamic. Now we can use models, and we can simulate the electrical and the process side, look at the correlations and test whether our deviations and our risks were correct. And as a little bit of a treat for you, come visit us on stand 110, because actually there is a model of the hydrogen value chain there, from the power generation, the production, the storage, the compression, and you can actually see it running in real time, and you can test those. And obviously, if we do get the product out of the pipe, the last thing we want is a spark. And trust me, for hydrogen, it only needs to be a very little spark. So pay attention to the electrical side. Make sure that you're earthing and bonding. That's probably the biggest risk that we see. Ventilation, make sure that you're purging and pressurizing the hydrogen out of contained spaces. Pay attention to classification, ATEX zones, because again, we want to limit the exposure and the potential of a spark, finding an ignition source. And then obviously we want to keep this process operating continuously and safely. So when I said, what can we do to mitigate those risks? We build layers of protection in defense in depth to stop that from happening. The first layer of protection is our control system. We want to control that process and that balance of plant in a safe state. Keep it within the safe operating window. If it starts to deviate towards an unsafe condition, we're going to get a high pressure or a high temperature. We want to alert somebody. So typically that would be an operator alarm. We expect the operator to take a response and an action, bring that process back into a controlled state. But we want to build a more robust, a more rigorous first layer of protection. We don't just want to rely on a process control system and the operator. Because there is such a close correlation between the energy and the electrical and the process that's being controlled, bring those two domains together. Use the information to provide a much more robust first layer of protection. If, for any reason, the process continues to get past that layer of protection, we're going to put our safe shutdown systems in. So we're going to look at our emergency shutdown. That might be a manual push button for somebody on the plant. It might be an automated system. So we're going to take an executive action. We're going to shut off the compressors, the electrical supply. We'll stop the feed water. We will try and bring that process back down to a safe state, which is off. And then we'll purge the hydrogen and get that out away from everybody else. The other thing you'll have is firefighting. Typically, you'll have firefighting, you'll have alarms, you'll have beacons, you'll have sounders. You might have a deluge system on there. So you'll have a fire and gas detection. That's a mitigation system, but it's another layer of protection. So again, you want a high integrity, high availability safety system specifically to ensure you take the process to a safe state. So, in summary, there are many safety considerations that you need to think about when you're looking at making a hydrogen facility safe. It all starts at the very beginning, those 4 questions. Eliminate, identify and eliminate the hazards, the risks. Remember, what can go wrong? What is the likelihood? What is the consequence? What do I have to do to mitigate that? And then ensure that you keep the system integrity. Do not let the product escape from the pipe. Avoid those ignition sources. If it does happen and hydrogen gets out, you want to make sure that you vent it, because jet fires are a key risk with hydrogen. It just takes one little pinprick, and because of the pressure, and the good news is that hydrogen, when it goes into a flame, goes upwards pretty quickly, but you can't see the flame. That's the big challenge with hydrogen. So the emergency response teams, who are not necessarily on site, but maybe from the community, need to be aware that this is a hydrogen incident because they can't necessarily see the flame. Isolate leaks. Again, the biggest thing we've seen is metallurgical. One incident was actually because a maintenance technician had refitted a pressure transmitter on a compressor. They just took one off the shelf, didn't realize it was being used in hydrogen. Metal embrittlement caused a leak, caused an incident. So again, leaks are important. And of course, training, not just of the people on the plant, but also the surrounding communities. Because again, these hydrogen plants are being put in, certainly when you look at the value chain where the point of distribution is, you're likely to be in a more residential area for the distribution for, say, vehicles or etc. So again, people need to be aware of the threats and the risks that they're managing. So with that, I'm Steve Elliott. It's been an absolute pleasure to talk to you this morning. Thank you very much for your time. Please connect with me on LinkedIn. Love to talk to you on Stan 110. With that, please come visit us, talk to us at Schneider Electric. We are here to help you. With that, thank you very much indeed.